Section 1, we started off with atoms, okay? What is an atom? How can we model the idea of an atom, okay? So we had 4 gentlemen that we looked at in particular. Which was the first atomic model we looked at? Dalton's, okay, very good. And what did that look like?
Just a solid sphere.
Just a solid sphere, right? Excellent. Dalton thought that atoms were indivisible. It was just a solid sphere, right? Similar atoms had similar properties, or different elements had different properties, right? So like the atoms of oxygen would have been different than the atoms of hydrogen, okay? And it was indivisible. Very good. So Dalton was first. What was the second guy? Thomson. Very good. And what was his model? Yeah, the plum pudding model. Excellent. Okay. So Thomson kind of had his electrons embedded throughout, kind of like a plum pudding model, or they're also like on the outside, right? So Thomson realized that the atom was not indivisible, right? It had positive and negative parts. Good. And then who was after Thomson? Rutherford. And what did he have? What did Rutherford have? Yeah, he had a nucleus, a positively charged nucleus, good. And then he also had what? What else did he have? So he had a positively charged nucleus, and he also had electrons, okay? But these electrons just kind of floated around, right? They didn't have much organization to them, okay? And then who is our last dude? Bohr, okay? Bohr is boss, okay? Bohr. Niels Bohr is, yeah, he's awesome. Okay, so he had a positively charged nucleus. And then he also had his electrons in what? What do we call these? What did Bohr have? What am I drawing?
In energy levels?
Yeah, perfect. Okay, he had the actual electrons in energy levels themselves. He studied emission spectra, remember? Okay, not a very accurate diagram, but this is kind of the rough idea of the models. Okay, so make sure you guys are able to identify the structure to the scientist, okay? That is really important, and that will be tested on, okay? So make sure you know that. Good. Any questions with that one? No? Excellent. Okay, next we had atomic structure, okay? So atomic structure being what actually makes up the atom. Okay, so who can tell me what the 3 things are that make up an atom?
Protons, neutrons, and electrons.
Excellent. Okay, so we have protons. We have neutrons. And we have electrons. Okay, who can tell me more about protons? Positively charged. Perfect. Positively charged. And where do we find protons? Are they around in orbitals?
In the nucleus.
In the nucleus, okay? Excellent. So protons are positive and found in nucleus. What else why are protons important? If I tell you an element has 8 protons, what could you tell me from that?
What the element is.
Perfect. So it tells us what the element is. So if something has 8 protons, it is automatically oxygen, always, okay? tells us what the element is. Anything else about protons? I think that's pretty good. Okay. Moving on to neutrons. What do we know about neutrons? Let's start off with the charge.
They have no charge.
They have no charge. Okay, good. And where are we going to find these guys?
In the nucleus.
In the nucleus as well. Okay, good. Okay, protons and neutrons both form up the nucleus. Okay, so we call these nucleons. Okay, don't worry too much about that, but that's just you might hear them referred to as nucleons. Okay, that's just because they make up the nucleus. Okay, so no charge, they're found in the nucleus. And these are not going to tell us what the element is, right? But what will neutrons tell us? What are neutrons kind of related to?
The mass.
The mass number, right? Good. So, yeah, we can find this from subtracting, so mass number minus atomic number. Okay, good. These will vary if the element is what? Is a what? An isotope. Excellent. Okay. Perfect. Good. And we'll talk about isotopes in a bit. Okay, and lastly, electrons. What do we know about electrons?
Negatively charged.
Negatively charged. Good. Where are these going to be found?
In energy levels around the nucleus.
Around the nucleus. Perfect. Okay. So found in energy levels / orbitals around the nucleus. Good. What else do we know about electrons? They're pretty important. Electrons, so remember the valence electrons? Valence electrons, these are involved in chemical reactions. Okay. And what do elements / ions always want to have?
A full octet.
A full octet. Good. Atoms always want a full octet. Good. And we have 2 electrons in first orbital. And then we have 8 electrons in other orbitals. Good. Good. So we've gone over atomic structure. We've gone over what actually makes up the atoms. Good. Questions so far? All good? Okay. So, question 3. How is the periodic table organized? Periods and groups. Excellent. Okay. So remember, periods go horizontally. So that's a period, this is a period, this is a period as well. So periods can tell us how many energy levels we have. Okay, that's really all I have to say about that. It increases in size as we go from left to right. Okay. Yeah, periods. Okay, good. Next are groups, and I just want to draw our attention to the 4 main groups we've talked about so far. So, what was the name of our group 1 metals?
Alkali.
Good. Okay, so group 1 is the alkali metals. Okay, they typically have a common ion charge of +1. What are our group 2 called? Excellent. Alkaline earth metals. And what is the common charge for our group 2 metals? Our alkaline earth metals? +2. Good, and then we're going to jump to our halogens, which are group 17. And the common ion charge on halogens, -1, okay, always -1. And what do we call the group 18?
Noble gases.
The noble gases. And what is their common charge? Sorry? They don't have one. Why not? They're non-reactive, absolutely. And why are they non-reactive? Think of our octet and our valence electrons. They already have a full octet, right? So they're happy. They don't want to give anything away. They don't want to take anything from anybody. They're just happy, okay? They have their full octet. They're good, okay? Make sure you're able to identify these groups. So if I give you a question on a final, for example, and instead of it being potassium, if I just put a letter A in there, I would say letter A belongs to which group? And then you guys would say letter A begins to the alkali metals, okay? Good. Okay. We already kind of talked about this, but what is an isotope? What is an isotope? Springfield Isotopes, remember, baseball team on The Simpsons? What is it? Not that. Not that. An isotope Okay, make sure you guys know what an isotope is. So an isotope is the same number of protons different number of neutrons. Okay, so I've given you the carbon 12, carbon 13, carbon 14 example. Okay, so, well, we can talk about it again. So, carbon 12, carbon 13, carbon 14. So it's carbon always, or well, in these three isotopes, anyways, it's carbon, right? How many protons does carbon always have? 6, right? Okay. Carbon always has 6 protons. So 6 protons, 6 protons, 6 protons. And then here's our mass number, right? So if we just do our mass number minus atomic number, that tells us the amount of neutrons. So in this case, 12 minus 6, we have 6 neutrons. 13 minus 6 is 7 neutrons. And 14 minus 6 is 8 neutrons. Now, what if we did it for neon 19, neon 20, and neon 21? Okay? Do these 3 on your own, please. Oh, and you guys don't have a periodic table, so I'll help you. Neon has a atomic number of 10. So what does that tell us? If it has an atomic number of 10? 10 protons, very good. So neon always has 10 protons. And then if we subtract our atomic number from the mass number, we get the amount of neutrons, right? Oh, it's gone. So our mass number is 19, our atomic number is 10. 19 minus 10 is 9 neutrons. 20 minus 10 is 10 neutrons. And then 21 minus 10 is 11 neutrons. Okay? So again, an isotope, same amount of protons, different number of neutrons. Okay? Make sure you guys know what an isotope is. Okay? Any questions regarding isotopes? All good? Great. Okay, next is valence electrons and the formation of ions. Okay, so cations, anions, what's the difference? They sure are. Okay, cations are positively charged. Good. And anions, conversely, are negatively charged. Okay, good. Give me an example of a cation. Something from this side of the table. Maybe I should also say that it's an electron donor. We're just kind of saying the same thing, right? Like if you're giving away something that's negative, you're going to become more positive, right? So it's kind of saying the same thing. It donates electrons, so it becomes positively charged, okay? An example of a cation would be, let's say, magnesium. and it has a common charge of +2. So it gives away 2 electrons. So if anions are negatively charged, they are electron acceptors. Okay, and who can give me an example of an anion?
Oxygen,
Oxygen. And the common charge for oxygen is?
-2.
Good. Okay, and if you're having difficulties remembering the difference between cations and anions, remember cats have pause, so cations are positively charged. Okay? Yeah. Okay? Energy level diagrams. Okay, so remember these. These show protons, neutrons, and electrons. Okay, you guys good if I move this? So energy level diagrams, these are going to show protons, neutrons, and electrons. Not to be confused with electron dot diagrams, right? Different things. Similar but different. In Asia they have the same, but different, right? So kind of similar but still different, okay? So let's do the energy level diagram for, we'll do something easy. Let's do fluorine. Okay, so fluorine from the periodic table. I see some of you guys have them out. It's over here. Brody, can you read from here? Yeah, it's tough. Okay, I know. I have bad vision too. So in this top right corner, we have a 9. That's our atomic number. So what does that tell us?
That there's no protons.
Excellent. Okay, so we have 9 protons. We have a mass number of 19. Okay, so 19 minus 9 protons equals 10 neutrons. And I don't care what order you guys do these in. Okay, whether you do protons first or neutrons first, it doesn't matter. Okay, then we're going to have our symbol of F. Fluorine. Okay, good. And then in a neutral element of fluorine, it will, if it has 9 protons, how many electrons will it have, Tanner? If it has 9 protons? 9 electrons, very good. Okay? So we're going to have 9 electrons, and remember, we have 2 electrons in our first orbital, right? And then 7 electrons in the second orbital. Okay. Now I would like you guys to do one for the sodium ion. Is sodium a cation or an anion? Cation. Okay, so it's going to give away electrons, so it'll become positively charged. Sodium is a group 1 metal, so typically has a charge of +1, right? Okay. Sodium has an atomic number of 11. So what does that tell us, Harrian? We do have 12 neutrons, yeah, but the atomic number tells us the amount of protons, okay? So it has an atomic number of 11, so it has 11 protons. Okay, Harrian observed that we have a mass number of 23, and then you subtract those 11 protons to find the number of neutrons, right? So 23 minus 11 is 12 neutrons. Okay, so then we'll do our symbol, Na plus. Okay, in the first orbital, we have how many electrons?
2.
2. Always 2, okay? 2 electrons in the first. In a neutral element of sodium, it would have 11 electrons because it has 11 protons, right? This is the sodium plus 1 ion, so it gave away one of those electrons. So instead of having 11 electrons, it only has 10 now, okay? So 10 in total, we have 2 in the first orbital, that leaves 8 in the second orbital, okay? And that is good, okay? When you're doing either an energy level diagram or an electron dot diagram for an ion, it should have a full octet, okay? If you do not have a full octet when you're doing it for the ion, it's a good indicator that you've done something wrong, okay? Okay, so those are energy level diagrams. Again, not to be confused with electron dot diagrams, okay? Remember, in electron dot diagrams, we only show what kind of electrons?
Valence.
The valence electrons, good. So the symbol, the elemental symbol, represents protons, neutrons, that's it. Represents the protons and the neutrons. Protons and neutrons and inner electrons. Okay, so these are only going to show the valence electrons. I think these are a little bit easier. Okay, so let's do the valence for potassium. And then we're also going to do it for the potassium ion. And we're going to do it for the chloride ion. Potassium is a cation or anion? Cation, so positively or negatively charged for potassium.
Positive.
Okay, and it's a group 1, so expect it to have a charge of +1. Chloride ion, is that an anion or a cation? Anion, good. And it's a halogen, so you expect it to have a -1 charge. Okay, so try these on your own, please. So our potassium, this is just a potassium atom. Okay, so potassium is a group 1 metal. So that means it has 1 valence electron. Okay, so this is what potassium is going to look like. Okay, remember we watched those videos on the reactivity of the group 1 metals, right? We dropped lithium and sodium and potassium in water. It was very reactive. It actually lit on fire, and in some cases it blew up the beaker. Okay, that's because it wants to get rid of that 1 electron. Okay, so let's move to the potassium ion, where it actually has gotten rid of that electron, right? So if it is given its 1 electron away, right? Now it will have a full octet, right? Because it just goes down to the next energy level. Okay, so that is what the potassium ion electron dot diagram looks like. Okay, and the chlorine ion, so chlorine is a halogen. It has 7 valence electrons normally, but it wants to take 1 more electron to have that full octet. Okay, so it would have 7 normally, but then it would take, it would have 7 normally, and then maybe it would take like that electron from the potassium, okay? And then you could get a compound potassium chloride, okay? So again, valence or electron dot diagrams only show the valence electrons. Energy level diagrams will show protons, neutrons, and electrons in the actual energy levels. Okay? Okay, compare and contrast between ionic and molecular compounds. But be like that. So, what is an ionic compound? We should all know this.
Metal and a non-metal.
Metal and a non-metal. Metal and a non-metal. Okay, so we could list off a lot of examples. My favorite one, sodium chloride. Okay, and just what do we know about ionic compounds? That's okay, I'll help you guys out. Okay, so it conducts electricity when melted or dissolved in water. It has a high melting point. What else? Net charge of 0. Okay, so you guys should be able to like know this at a minimum if I ask you to compare the differences between ionic and molecular. Okay, so ionic compounds, metal and a non-metal, it conducts electricity when melted, or if it's dissolved in water, has a high melting point, and has a net charge of 0. So if a if ionic compound is a metal and a non-metal, what is a molecular compound then?
2 non-metals.
2 non-metals. And it's kind of like, almost like the opposite of this, right? So it is unconductive. Typically, there are going to be exceptions to the rule, but typically it's unconductive. Okay, it has a low melting point. And it does not necessarily need to have a net charge of 0. Things I forgot, molecular compounds, they share electrons. Ionic compounds, we have transfer of electrons. Share electrons, low melting point, unconductive, 2 non-metals. An example of a molecular compound. Does anyone come up top of your head? Carbon monoxide? Cool. Absolutely. Okay, so make sure we know the differences between ionic and molecular compounds. Okay. And again, I'm going to post this to the classroom after this, okay? So you guys can look at this if you missed anything. Okay, and then let's go over acids and bases. So let's start with bases because I already have the blue marker in here. So pH greater than or equal to 7? That was a question. Does it does it have a pH greater than 7 or a pH less than 7?
Greater.
Greater than 7. I know that kind of looks like that. And then conversely, acids have a pH greater than 7 or less than 7? Less than 7. Okay. How can I tell a base from an acid?
Bases are bitter.
Bases are bitter. Okay, good. So yeah, bitter. Bases are bitter. They're kind of slippery if you feel them. They're slippery. They typically do not react with metal. Okay, that's why they're like used as a cleaning product, right? You don't want to have like a gnarly chemical reaction as you pour your cleaning solution onto something that's metal, right? Bases, we have a hydroxide present. Awesome. Turn litmus blue. Okay, I think that's good there. And an example of a base? Baking soda. Yeah. So that'd be like a bicarbonate. Okay, I'm just gonna do an easy one for us. Like I'm just gonna do KOH. Okay, potassium hydroxide. Baking soda is absolutely a base. This one's just a little bit easier for us to see because it has that hydroxide present. Okay. Okay. So conversely, acids are sour. They will. They're what? Sorry.
Corrosive.
Corrosive. Yep. Reacts with metal to form gas. Turns litmus red. And typically we have hydrogens present. And an example of a base, the HCl, hydrochloric acid. Great example of a base. Almost there. Almost there. Just gotta go over some naming rules. And then we're done with our review.
Hey, hello, one quick.
Yep, of course. Okay, so as we're naming different types of compounds, we have different rules for naming those different compounds, right? So first thing, so step 1, identify the type of compound. So the options would be ionic compound, molecular compounds, acid, or a base. Okay, so IC is ionic compound, MC is molecular compound, and acid or base is acid or base. Okay, and then we're going to have different naming rules for each one. So for ionic compounds, this was first thing that we named. So cation stays the same. Anion ending is changed to fluoride. Okay, so for example, if we have potassium and fluorine, so KF, potassium and fluorine becomes potassium fluoride. Okay. Multivalent ionic compounds. So remember these Roman numerals indicate charge on cation. So for example, if we had, okay, so Roman numerals, and then we need a net charge of 0. I should have mentioned that up here too. Net charge of 0. Okay, and again, because it's ionic, we need a net charge of 0. Okay, so my example is going to be iron 2 chloride. Okay, so iron 2 chloride. Again, the Roman numerals indicate the charge on cation. So I know the charge of my iron is +2. Chloride is a halogen, so it always has a charge of -1. So for this to have a net charge of 0, I'm going to need 2 of the chlorides. Okay, so then I go FeCl2. Okay. So yeah, Roman numerals indicate the charge on the cation. That's the big takeaway here. Okay, molecular compounds. So again, molecular compound is between 2 nonmetals, right? So how do we name molecular compounds?
With the prefixes.
With the prefixes, okay? So I will give you guys those on quizzes and stuff. So use prefixes to indicate number of atoms. And let's use our example of carbon monoxide. I like that one. Okay. So again, if the first atom or the first element has 1, it's no mono, right? So in this case, it is just carbon. And then on the second element, we only have 1. So then we go carbon monoxide. Okay. Not monocarbon. Not. Okay. Carbon monoxide. Okay. If we had N2O, that would be dinitrogen monoxide. Okay, polyatomic compounds. If it's a polyatomic ionic compound, we need to have a net charge of 0, of course. If it's a molecular polyatomic compound, we would use our prefixes to indicate that. Okay? But if we're just naming polyatomic compounds, do not change the ending of a polyatomic compound. Okay, and then you would just use your polyatomic, your table of polyatomic ions. And you just use your table of polyatomic ions to help you name those. All right, almost there. You guys have been great. Okay, naming acids and bases. This is really our last one here. So naming acids. So of course, first you have to recognize if it's an acid or a base or an ionic or a molecular compound. Okay. If it is an acid, so if you're given like the name, so if you go from like hydrochloric acid, okay, or if you're just given like the symbol, so you just name it as you normally would. So let me give you an example. So let's say we have HSO4. Okay, so this would be hydrogen sulfate. So name it as you normally would, then use naming acid chart. Okay, so we have hydrogen sulfate. Hydrogen sulfate becomes sulfuric sulfic acid. Okay, so I just looked at the compound, named it as I normally would, hydrogen sulfate, and then because it's an acid, you take it to the naming acids chart, which you guys will be given, and then you go, okay, I have hydrogen sulfate, and that becomes sulfic acid. Okay? Bases are a little bit easier to recognize and name. So, yeah. Name it as, so just recognize OH. This is hydroxide. Okay, and then other than that, it's just like naming an ionic compound. So, for example, let's do MgOH2. Okay, this just becomes magnesium hydroxide. All right. How are we doing? Good. Helpful review? Yeah? Got reading week brain? Word. Okay, last thing we need to talk about today. Again, make sure you guys are able to use a solubility chart, okay, to determine if ionic compounds will dissolve in water. So let's just do, for example, we can do, I don't know, let's do barium sulfate. So BaSF. SO4. Okay, so if you use your polyatomic ion chart, you'll see sulfate has a charge of -2, barium has a charge of +2. So then you would find your sulfate ion at the top, right here. I see that most is soluble. So if it's not on this list, it's going to be aqueous, but then I'm going to continue down, and I see the barium +2 cation is on the low solubility list. So that means this is a solid, or a precipitate will form, okay? So make sure you guys are able to use your solubility table. The majority of you guys did really good with that on that quiz that you guys wrote before you left. Okay, so make sure you can use that. And then lastly, we have our elemental diatomic / polyatomic molecules on Earth. Does anybody remember those guys? Remember our 7 here? Sinister 7. So phosphorus, well, sulfur, phosphorus, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So to answer this, the first part of this question, why are the unstable ions usually not found? Well, that's because they are unstable on their own. More stable making a compound or molecule. Okay, so yeah, like the ions themselves, so like oxygen, the oxygen anion, O-2, is very reactive, okay? So it's going to find something to react with, and if it finds another oxygen anion, it's happy, okay? They can share electrons, and they'll both have a full octet, okay? Same with nitrogen and fluorine, etc. Okay? Our diatomic molecules, we have 7 of them. So hydrogen is one, and then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay? So we have H2, and then we have N2, O2, F2, Cl2, Br2, and I2. 1, 2, 3, 4, 5, 6, 7. And in the polyatomic molecules, we have P4 and S8. So if you ever see like elemental phosphorus, they mean P4, or elemental sulfur is S8. Okay? These are going to be important when we get into predicting chemical reactions. Okay? So keep these on the back burner.